Okay, so once we've accepted the idea of orbitals and we've accepted this organization of the periodic table, it becomes really easy to do electron configurations quickly using the periodic table. So the key is to remember that the left two columns are the S block. Also helium is part of the S block. This right block over here is the P block. The middle section is the D block, and the bottom section is the F block. Now, the F block is really not very important for IB questions. You won't be asked to do any configurations that include F orbitals, but we should still know that's called the F block because occasionally on paper 1 they might ask you which of the following elements is in the F block, and then you just need to know which section of the table you're looking for. But for our purposes, it's mostly important to know S, P, and D. And what I mean by it's easy is that as you read from left to right, so if I go group 4, right, then I'm thinking this I know is S1 because I'm in the S block and I'm in the first group of the S block. And then I know the second column will all have S2 at the end of their configurations because I'm in the second group, second column of the S block. If I'm in the P block, I know that I'll be ending my configurations in P1, P2, P3, P4, and so on, all the way out to P6, depending on which column I'm in. And with the D block, with a few exceptions, which we'll cover after we get the basics done, we should know that it's D1, D2, D3, and so on. Okay, the one trick to remember about the Ds, and this is the weird bit for Ds if I go ahead, the idea is that these energy levels, we know they're converging as we go to higher energy levels. And so what actually happens is that for atoms, it ends up being lower energy for electrons to occupy the 4s orbital before they occupy the 3d orbital. So we knew that the 3d orbitals can exist. We know that because of the mathematical equations of quantum mechanics that tell us that there are 3 sublevels in the third energy level. There's the 3s level, the 3p level, and the 3d level. So those are the different sublevels, and within them there are orbitals. But it turns out that for these electrons, it's actually slightly more stable, slightly lower in energy to occupy the 4s energy level before they occupy the 3d level. Now the 4s is a bigger orbital. If I were to attempt to draw a picture, then my 4s orbital would be larger than the 3d orbitals. 3d orbitals, remember, have these wacky clover-like shapes, or they have rings. So the 3d is higher energy, but physically speaking, it's inside of the 4s orbital. So 3d is inside of 4s. And what that means is that the 3d electrons are never valence electrons because d electrons are always inside. So 3d electrons are core electrons, or inner shell electrons. They are not valence electrons. So we'll see as we do some practice, we need to be able to count valence electrons. And we'll see that as a result of this D being on the inside, we never end up getting more than 8 valence electrons. So although the third energy level and above can hold more than 8 electrons, there is still something special about the octet. It is the maximum number of valence electrons that we can ever have. Okay, so let's try a couple of those D block ones, and I'll just do noble gas configurations for the sake of speed. Okay, so down here I have vanadium. Let's just jump right into that one. Now I can already see from where it's positioned that it's the 1, 2, 3. It's the third box over in the D block. So I'm going to end my configuration in D3. Now if I want to figure out the noble gas, I look at the last noble gas that I passed. So that's AR. So I will start vanadium's configuration with an AR in brackets. This is if I'm doing a noble gas configuration, not a full configuration. And then I have to do everything after AR. So the first thing I get to, I read it left to right like a book, is the 4s block. And I know that both of these are going to fill first. So I write 4s2. And then I know that I have 3d d electrons, so d3. And the one trick to remember about that d, again, is that the number is always lower. You'll also see on the exam, the IB is fine if you want to do it this way. You can write the d electrons first and then the s electrons. I find that confusing because I'd rather write from left to right in the order that they fill, but both will be presented to you and both are acceptable. In terms of valence electrons, you're looking for the highest number energy level. So the highest energy level is the fourth. So the valence shell in vanadium, the valence energy level is the fourth PEL, the fourth principal energy level. No matter how I write it, I should see that 4 is the highest number. So those are the outermost electrons. So vanadium has 2 electrons in its valence shell. So it has 2 valence electrons. Let's try another one that's past it. So for example, let's try germanium. Okay, well, germanium is in group 14. It's in the same group as carbon and silicon. And so already in the past topics, we would have said, well, that has 1, 2, 3, 4 valence electrons. We're going to see that that's still true. So this column we associate with 4 valence electrons. And so that shouldn't change with our new rules about configurations. So if I do germanium, then noble gas, I'll start with argon in brackets, and I'll start at the left-hand side again. So again, I start here with my 4s2. I'm in the 4th row. First, I go past 2 s blocks, so 4s2. Then, in total, there are 10 boxes in the d block. So I'm going to write 3d10. All of those are filled to get to germanium. And now I'm in the p block. But remember, now I'm back to my outer shell. It's only the d that does this inner shell thing that's one behind. We already filled the 3p. The 3p was up here when we did aluminum silicon. This is the 3p. This was the 3s. So 3s, 3p. Then we did our 4s. So now when I start to fill these next ones, I'm in the 4p. And so gallium would be 4p1, germanium is 4p2. So this is the noble gas configuration of germanium, and its valence electrons are the ones that are in the 4th energy level, because once again, the 3rd energy level, is inside of the 4th energy level. It's not on the outside. So I've got 4 valence electrons. If I was going to draw an orbital diagram for germanium, then I would do 1 box for the 4s, and that box is full because it's 4s2. I would draw 5 identical boxes for the 3d, and those are all full, 3d10. And then I would draw 3 boxes for the 4p, and there's only 2 electrons there, so following Hund's rule, I always put 1 in each box before I pair them up, and I draw them with the same spin, so they're all pointing up. So this is the orbital diagram for germanium. Again, I'm only showing the orbitals past the noble gas, and that's usually what they'll ask you to do as well on the IB exam. If you go ahead to this page here, there are some good practice of this concept. So this will be the homework, and I will post the solutions.